Welcome to NGVEX Explainer.
Hey everyone, what actually makes a 3D printing material truly stand out? Welcome to this explainer. Today, we're diving into the absolute benchmark of high-performance additive manufacturing. If you're used to everyday plastics, well, get ready, because it is time to level up.
Seriously, have you ever hit a wall where standard plastics just completely fail under extreme stress? If you're needing something vastly stronger, noticeably lighter, or highly chemically resistant, there's actually a premium, aerospace-grade solution out there. Meet the Ultra-Polymers.
So, what exactly are we talking about here? When we say ultra-polymers, we're referring to a very specific family of high-performance thermoplastics known as PAEK. This lineup includes PEEK, PEK, and their carbon fiber reinforced variants. These definitely aren't your typical hobbyist filaments. These are mission-critical, engineering-grade polymers designed for extreme temperature resistance, incredible chemical stability, and mechanical durability that literally rivals metal. Now, let's put this into perspective. Standard plastics like PLA or ABS, they're great for general prototyping, sure, but PLA gets soft at just 60 degrees Celsius. Ultra-polymers, on the other hand, maintain their structural integrity at a blistering 260 degrees for continuous use. Plus, they're inherently flame retardant without needing any extra chemical additives. It's just a monumental leap in capability. And the strength is just off the charts. Standard PEEK is already a powerhouse, right? It's got a tensile strength of around 100 megapascals. But when you introduce continuous carbon fiber into the mix, that number skyrockets to a staggering 212 megapascals. Basically, you are entering the territory of replacing machined aluminum parts entirely.
To quickly summarize this superhero-level performance profile, we're talking at 260-degree continuous use temperature, chemical resistance that's actually comparable to nickel steel, inherent biocompatibility, and a flexural strength of 335 megapascals for the carbon fiber version. These polymers can endure fire and harsh acids without even flinching.
Section 1. Industry Applications. Proven in the field. It's no surprise that the aerospace and automotive sectors rely heavily on these materials. In aerospace, every single ounce saved translates to massive fuel savings over time. By utilizing PEEK, engineers are actively replacing heavy metal brackets and engine components with lightweight parts that boast an incredible high strength-to-weight ratio. Over in the medical field, PEEK's inherent biocompatibility makes it the absolute ultimate choice for surgical implants and devices. Because it resists thermal degradation so well, it maintains its precise mechanical properties even after going through hundreds of high-temperature sterilization cycles in an autoclave.
Section 2. The pre-flight checklist. Beating the moisture problem. Now, if you're going to print with this stuff, moisture is your ultimate enemy. If you skip this mandatory drying protocol, steam will literally bubble in your hot end and completely ruin the part. Think of it like a strict pre-flight checklist. First, you have to aggressively dry the filament in a thermal chamber at 120 to 150 degrees Celsius for 3 to 6 hours. Next, transfer it directly to an airtight dry box to keep humidity below 20%. And finally, you have to print directly from that dry enclosure. No exceptions.
Section 3. Advanced Printing Parameters.
Now, getting commercial-grade results demands some pretty serious machinery. To extrude PEEK, you need blistering nozzle temperatures. We're talking up to 450 degrees Celsius, along with the print bed cranked up to anywhere from 120 to 160 degrees, and an actively heated chamber to prevent the part from warping. PEEK is slightly lower, but it still demands an active 120-degree chamber.
Now, you might be wondering about the difference between the two. While both are in the PEK family, they actually print quite differently. PEEK has a much faster crystallization rate, which makes it highly rigid, but also incredibly prone to shrinking and warping during the print. PEKK, however, features a slower, more tunable crystallization rate. That makes it significantly more forgiving, giving you better layer adhesion and way less warping. So here is your essential hardware checklist for these ultra-polymers. You absolutely must have an enclosed active heated chamber and a high-temperature heated bed. Also, if you're printing the carbon fiber composite variants, hardened steel or ruby nozzles are mandatory. Standard brass nozzles? Yeah, they will get eaten for breakfast by those abrasive carbon fibers. And finally, you'll need post-print annealing capability to really lock in that maximum mechanical strength. To bring this all together, it's worth looking at what industry experts say. They note that, quote, PEEK often provides a solution when lower-cost alternatives cannot meet performance requirements, one of the most capable materials available for additive manufacturing.
Basically, when your environment is just too hot, too corrosive, or too demanding, ultrapolymers are the uncompromising answer.
Ready to elevate your 3D prints? You should definitely try Ultra-Polymers today. And that wraps up this explainer. We've seen how these materials basically shrug off fire, harsh chemicals, and extreme mechanical stress. But I want to leave you with this one thought. If we can now 3D print parts stronger than metal right from a desktop enclosure, what massive, heavy metal industry is going to be fundamentally disrupted next? Thanks so much for joining me, and keep innovating.
If you enjoyed this video, don't forget to like, subscribe, and turn on the notification bell so you never miss our latest engineering explainers. Thanks for watching, and I'll see you in the next video.